Hello, folks. We are going to jump into 6-7 today, which is about rational functions and asymptotes. And we're going to start right away and look at a function that we are used to working with, and that is f of x equals 1 over x. Now, we've explored what this looks like. We know this is that hyperbola that goes through the point 1, 1, and 2, 1/2, 1, or 1/2, 2, and so on. So you end up with this curve that does this and approaches 0 this way and approaches infinity that way and goes through that point again over 1 down 1, over 2 down 1/2, 1/2 down 2. So you get that curve that does this. And excuse my graph being a little wavy, but that's what we get. And one thing we haven't talked about with this graph, I think we've discussed it, we haven't drawn them in. And what we're going to be doing with rational functions now is drawing in the asymptotes. All right, so we have an asymptote, a vertical asymptote, that goes through 0. Now we know that x equals 0 is a vertical asymptote. It's a place where this is undefined. That's what an asymptote is an x value where our function is undefined. And it's undefined because in the denominator here, if I put 0, I get 1 over 0, and we can't divide by 0 or the world would end. So we know that x equals 0 is a vertical asymptote, all right? And we've kind of done this work in the past. I know you have, but I just want to remind you of a couple things with vertical asymptotes. Vertical asymptotes are going to happen where the denominator is equal to 0. And in this case, and we always write them as an equation of a line. We draw them as this dotted line. All right, so it's an equation of a line. And we write it as x equals 0. So vertical asymptote for this graph is x equals 0. It's the only one. All right. We also have horizontal asymptotes. And in the past, when you've looked at these, you've just kind of done it by inspection, is what we'd say, is you looked at it and said, it looks like it's approaching this value from as x gets really big and y gets really big. The values of the function are approaching a single value. In this case, that value would be 0 again. And what's happening as we watch this, when we look at 1 over x, as x gets really big, as we look at the end behavior, as we've discussed before, we look at the end behavior of this, it's approaching 0 as x approaches infinity. As x approaches negative infinity, it's also approaching 0. So as we look at the end behavior of this graph, if it approaches a single value, that is a horizontal asymptote. And those are always going to be I should say always going to be a horizontal asymptote. A true horizontal asymptote will always be y equals, and in this case, y equals 0. So these are your two basic asymptotes for this graph. Now, we've done some other work with this where we've also said, all right, we know how to translate this, right? So let's go to another grid and let's look at another function. If I gave you y equals 2 over x plus 1 minus 3, how would this graph change? Well, we know that this x plus 1 is inside the function, so that's left 1. This is down 3, and this is the multiplier of 2 is a vertical expansion by a factor of 2. So what is that going to look like? Well, these two things right here, this right here, if the entire graph is shifting left 1, well, isn't that going to make this vertical asymptote shift left 1? So we would have to have a vertical asymptote now here. If every point on that original graph, that graph we had before, shifts left 1, then it stands to reason that this would. Again, looking back, if this is at y or x equals 0, then and every point on this graph and this piece here moves left 1, then this has to move left 1. So we have a vertical asymptote now where x plus 1 equals 0 or at x equals negative 1, right? It's where that denominator equals 0. Now, our horizontal asymptote, if everything in this graph is going to shift down 3 as well, it's going to shift down 3, well, that means my horizontal asymptote has to shift down 3 as well. So again, we used to have it at y equals 0. Now it's going to be y equals -3. So we would have our horizontal asymptote going across here. And from this intersection of the asymptotes, normally we'd go over 1, up 1, but because we have the multiplier of 2, we know we're going to go over 1, up 2. All right, it's going to pull this graph away from that axis that we've created with the two asymptotes. It's still going to have asymptotic behavior. It's still going to go up towards this and down towards this. It's just going to be farther away. Whoa, I did not want to do that. There we go. Sorry. It is going to go, there we go. That's what I wanted. Again, back 1, down 2, and it'll have this behavior. I should have extended that down a little bit. And so we'd have this graph now. All right. So again, looking what we have here, we could have seen this. We can see what's going on here, and we can find out what the vertical and horizontal asymptotes. That's what we're going to ask you about throughout this section, is to find vertical and horizontal asymptotes. Vertical asymptotes we can always find by finding where the denominator equals 0. And horizontal asymptotes, we're going to have a few different approaches to that as we go. Let's look at another function. All right, this is f of x equals x over x minus 3. So now looking at this, I think most of you would be able to say, all right, I think at x equals 3, we're going to have a vertical asymptote. All right, and you would be right. All right, that is going to be the case. A vertical asymptote is going to happen at x equals 3. So at x equals 3, I can draw a vertical asymptote. But what about the horizontal asymptote? Can we figure it out from this? Well, we can. All right. Looking for this horizontal asymptote, we can do something, because if we can get it in that form like we had in the last problem, where we can see the shifts, everything will work. Well, if you look at x over x minus 3, that's a division problem, isn't it? It's x divided by the quantity x minus 3. So let's do that. If we do x divided by x minus 3, what do we get? Well, first we'd have 1 times this, and that makes x minus 3. This is, you can call it plus 0 if you want. And then we subtract, we get a positive 3. So we can't make x go into this, so we do plus 3 over x minus 3. Well, look at this. Isn't that the equation y? This is just another form of that same equation we have up above. We can write this as 3 over x minus 3 plus 1. Well, now we see our vertical asymptote of 3. We see it has a vertical expansion by a factor of 3, and it goes up 1. So if it goes up 1, I know my horizontal asymptote now is y equals 1. And I can draw that in. I also know now that instead of going over 1, up 1 from here, I'm going to go over 1 and up 3 because of that vertical expansion by a factor of 3. And I can sketch in that asymptotic behavior, arrows at the ends, and do the same up this way. I've lost, there we go. All right, so same up this way. Back 1, down 3. I can draw that in. And that in. Don't cross your asymptotes. All right, so we get this. And again, we got that just by dividing this, right? Doing the division that was represented in the problem. Let's do one more like that. What if it gets uglier? What if I give you y equals 3x plus 4 over, let's say, x minus 2. All right, again, I know right off the bat that for my vertical asymptote, I've got x equals 2. So x equals 2, I draw in a vertical asymptote. All right, now, horizontal asymptote. I have to do a little bit of work. So I'm going to do x minus 2 divided into 3x plus 4. Again, this long division coming in handy for us, guys. So x minus 2 into this, I can do 3, right? X goes into 3x 3 times, so 3x, and then minus 6 when I multiply this out. subtract. When I subtract, this becomes plus a positive, so I get 10. So this is going to be plus 10 over x minus 2. So again, we've got this equation rewritten now as 10 over x minus 2 plus 3. So what do I know about my horizontal asymptote? Well, I know it's going to be at y equals 3. It goes up 3. So I'm going to have that up here now, and this is going to be going up. Now, what do I know about my vertical expansion? My vertical expansion is going to go over 1 and up 10. So I'm just going to say this is 10 up here, right, on my scale. And so, or it would have to be 13, I'm sorry. Let's say that's 13, so over 1 up to that 13, and we would draw our graph in back 1, down 10. And again, we'll just say it's down here. I don't want to take your time by resketching this grid. Okay, so we have that as our vertical asymptotes and our horizontal asymptotes. Okay, so I want to go back and look at something here. If you notice a characteristic of this function, the degree of the polynomial on top is the same as the degree on the bottom. This is the degree 1 because this is to the highest power is to 1. This is degree 1, highest power to 1. Same here, degree 1 over degree 1. This is our, with this one, we've got degree 0 over degree 1. So it's something a little bit different, all right? Now, actually, I'm sorry, this is minus 3. That is not even one we're looking at. This is not in true rational expression form. So just look at these. Degree 1 over degree 1, degree 1 over degree 1. Now let's look at one that is going to be a little different. All right, so y equals 5x squared plus 2 over 3x squared minus 1. Well, now we've got degree 2 over degree 2. And we can still find our vertical asymptote right away because, again, what do we know? It's where 3x squared minus 1 equals 0. It's not as obvious as our other functions, whether that were degree 1, but I can still solve this. 3x squared equals 1, x squared equals 1/3, and that makes x equal to plus or minus 1 over root 3, or you could say, and more appropriately say, root 3 over 3. So at x equals positive root 3 over 3, and x equals negative root 3 over 3. And what is that value? Let's see. Square root of 3 divided by 3 is about 1/2. So both on this side and this side, both positive and negative, root 3, we would have, whoops, that's kind of veered off. We would have these asymptotes to sketch this graph. All right, so these are our vertical asymptotes. X equals root 3 over 3, and x equals negative root 3 over 3. Remember, we have to write these as equations. So those are our vertical asymptotes. Well, how do I find our horizontal asymptotes? Well, let's take a look at this with our graphing calculator. All right, and I think I'm going to have to reshare this. So now you see my calculator. If we go to y equals, and let's clear that out, and let's put this one in. Putting in rational functions, you got to make sure you separate top and bottom, the numerator and denominator, by parentheses so that it does the entire quantity divided by the entire quantity. That divided by, on the bottom, we would have 3x squared minus 1. And let's take a look at this. Well, there's our asymptote at negative 1 root 3 over 3. And you see the asymptotic behavior at positive root 3 over 3. But look at this. We can see that these values are approaching something as x gets really big. So let's start to look at that. If we go up, or let's go down, and we go out to x's that get really big, see this number is decreasing, decreasing, decreasing. It keeps decreasing as we go, getting closer and closer and closer. It's going very slowly, notice, but it seems to be getting closer to 1.666. We got to 8, 7, 6. So it looks like 1 2/3, right? 1.66667 or 1.67. It looks like it's getting closer and closer as x goes to infinity. So again, looking at this, it looks like we have a horizontal asymptote, right? Because this, as x gets really big and negatively really large, both of these things are approaching that value. It looks like we got a little piece in here we're going to have to deal with in a minute. But let's look at this horizontal asymptote. That horizontal asymptote, just to give you a heads up, is this value. It's what it looked like, didn't it? 1 2/3. Same degree, top and bottom. Look at the lead coefficients. They're going to tell you. And that happened back here, too. If you look at back here, lead coefficient 3/1 gave me y equals 3. You look back here, x over x would be 1, right? Y equals 1 was my horizontal asymptote. So this is a pattern that holds. If you have same degree of a polynomial on top and bottom, you can just take the lead coefficients. We've talked about these terms, these words before, and those are going to be your asymptotes. So this would be at 1 2/3. We'd have y equals 5/3 as our horizontal asymptote. Again, we write it as an equation. And we know up here, we have this going this way. And whoops, sorry, it was on the top up there as well. It was because of the squaring. Let's stay positive out here. And then we've got to investigate that other piece. So let's look back at that graphing calculator. All right, let's zoom in on this piece here. So let's zoom in let's zoom in right here. It appears it goes up to about 2. And that's all I'm really looking for from you guys is I want you to estimate or try to find out where that goes. And because we are just doing a sketch, it looks like it comes up to -2. And then it has asymptotic behavior with the asymptotes we'd already drawn. So we can sketch this giving both the vertical asymptote and the horizontal asymptote. We need these and these. This is what they're going to ask us. Find any asymptotes. Any vertical asymptotes, find any horizontal asymptotes. You need to be able to do that. And then they'll say sketch the graph. So we're just looking at a good sketch of the graph. All right. And again, you could have found at -2, if we go back to our graphing calculator, I should be a little bit better with that. If I go to my table and I got to go all the way back here. If we go back to the value at 0, we can see what it is. It is centered at 0, so we can see that that is something we can look at. Just get back to 0 here real quick. There we go. All right, at 0, we do have -2, so that was accurate. All right, and that's a good sketch of this graph. And again, that is when we have degree the same, top and bottom, we can take those lead coefficients and use them as our y equals. All right, so now what happens if we don't have something that nice, where the degree top and bottom isn't the same? All right, what if we have degree of the numerator less than the degree of the denominator? All right, well, if that's the case, you'd have something like this. And this is kind of a nice thing too, because if we approach this and say, all right, I want to find vertical asymptotes, always going to be, no matter what the degree situation is, top and bottom, vertical asymptote is going to happen when the denominator equals 0. So x squared equals 4, x equals plus or minus 2. So writing my vertical asymptotes would be x equals 2, x equals -2. Notice I wrote them both out. This is what we're going to ask you to do on quizzes or tests, that you've got to write both of these out as equations. All right, horizontal asymptote, there is a trick here too. This one's easier than the last one, because if the degree on the top is smaller than the degree on the bottom, well, this degree on the bottom is going to grow exponentially faster, right? So the number on the bottom is going to get large much quicker than the number on the top, sorry. And that means overall, this value is going to be going down, isn't it? It's decreasing because this value is only increasing by 1. This is increasing exponentially. This number is going to get closer and closer and closer to 0. So when you have degree on top, less than degree on the bottom, it's always going to be y equals 0. So again, we can sketch a couple things in here. You've got to draw your asymptotes in. It's one thing I want to make very clear too, guys, is that we need to have these drawn in. So at 2 and -2, I draw these in. And then I have y equals 0. So I've got this drawn in. I've already got my kind of framework. Now I need to know what it looks like. Well, this is where we go back to here. Let's go into y equals, clear that out, and let's do this one. We can do x divided by x squared minus 4. And I'll do a standard zoom on this. And here we go. So we see that asymptotic behavior on this side. And this side. And then we look like we're going through 0, 0. Let's take a good look at this again. Go to second table. At 0, we do go through 0, 0. There are some other points if you wanted to use them. At 1, you got -1/3. At 4, or I should say, at 1, you've got -1/3. At 3, you've got positive 0.6. Again, you can use some of these values if you want to, going upwards. It looks like this is symmetric, so we can do that. We're going to be at about 1/3 here and going upward, and 1/3 here going downward, right? And again, if we look at that picture again, looks like a pretty good sketch. All right, that's what we're expecting to be able to do, guys. All right, that's degree of the numerator less than the degree of the denominator. All right. Last one. Well, we've done where they're equal. We did where the top is smaller than the bottom. Let's do the next one. All right. And of course, that is going to be where the degree of the numerator is greater than the degree of the denominator. All right, so what's that going to look like? Something like this. Y equals, of course. And we'll do something here. So what happens here? Well, again, I can follow the same thing and say my vertical asymptote is going to happen where the denominator equals 0. It's just that. Got our vertical asymptote done. All right, x equals 0. I can draw it in. We have that denominator. Now, the horizontal asymptote. Well, let's look at this graph briefly here. And when we look at this graph, well, let's do it. Y equals, let's clear this out. And let's put x squared plus x plus 1 and divide it by x. And let's graph this. Well, we can see our x equals 0 asymptote, but I don't think there's a horizontal asymptote. But if you look right here, it doesn't look like this is a line going here. This is something we call, when we have a degree of the numerator greater than the degree of the denominator, we get what can be called a slant asymptote. So no longer, in this case, do we have horizontal asymptotes. We've got slant asymptotes. All right, and a slant asymptote, we can find out what that is, again, by doing division. All right, if I divide x into x squared plus x plus 1, I would get x, which would give me x squared. Subtract, I get 0, bring down the x. That would give me a positive 1, which then I would have, let's see, 1 times x would be x. Subtract, I get 0. I bring down 1. 1 can't go in here, so I say plus 1 over x. This is a description of what happens. This is basically the same equation as what we had up at top, right? This is it in a different form. Y equals x plus 1 over x is rewriting this in a different form. Just like we did in the beginning when we did that division, we rewrote it in a form that helped us draw it. Well, this form helps us too, because what you see in that graph is this line is the line, and let's draw it in so you can see this. It is the line x plus 1. Where do I get x plus 1? Well, look over here. These terms before they go rational. And if I graph that, watch what happens. Doesn't that look like it? This is approaching that line. It's the difference between our actual graph and the line y equals x plus 1 is this term right here. This term right here is that difference. It's never going to hit y equals x plus 1, but it's going to get really close as this number gets to 0. So this is a way of rewriting this graph to say, hey, I can see that this thing is approaching x plus 1, which I know goes through 1 at a slope of 1. So it would be doing something like this. So I can draw this slant asymptote in. And then, again, looking at my graph, it looks like up in that upper quadrant is where I'm going to be drawing. Up in here, it's going to be doing this. And down here, doing this. So we have this graph with the asymptote. Again, this graph will get infinitely close to x plus 1, but not hit it. So those are our three cases, so to speak. Degree the same top and bottom, degree less on the top than the bottom, degree greater on top than the bottom. All right, let's do another one. Let's do y equals x squared minus x minus 12. And I should probably get a grid down here. I wonder when it's going to overload on me. All right, so we've got this. I'm going to move that out of the way. Move this around a little bit. All right, so we've got this now. This over, whoops, get my lines back. That over x minus 4. This one. Now, this appears to have the graph that would be x squared over x, so I could divide this, right? So let's take a look at that. So far, it looks like it should have a vertical asymptote at x equals 4. But let's take a look. X minus 4, because we know we're going to need the horizontal asymptotes also, into x squared minus x minus 12. So if I do this, I know that's x. So x times x is x squared. X times negative 4 is negative 4x. And subtract. So I get 3x minus 12. Right, I'll bring down the next term. X going into 3x is a positive 3. And I get 3x. 3 times negative 4 is negative 12. So we could rewrite this. This is actually goes in evenly. So I have this. If it goes in evenly, then we don't get a slant asymptote. In fact, we don't even get this vertical asymptote, because what happens here? At x equals 4, we don't have an asymptote. We just have an undefined value. This graph is going to look like y equals x plus 3 everywhere except x equals 4. All right, this is going to look like it's going through this. Let me do something first. I want to drag this down a little bit. We're going to be up here. All right, so this is going to be going through 3. This graph is, and it's going to be going up until it hits 4. When it's at 4, we know that the original function, if you put 4 in, you get an undefined value. But if it had been x plus 3, if I look at this graph is going to look like x plus 3 everywhere except at 4, 7, because if I plug in 4 here, I would get 7. So at 4, 7, what we do is note that there's no value there with a big circle. And then we just draw, whoops. line going this way, a line going that way, and with that thing here we call a hole. So it has a hole at the point 4, 7. All right, so we have to note that hole with an open circle. So this doesn't have, if they ask us about asymptotes, none. No vertical asymptotes, no horizontal asymptotes. It does have a hole at 4, 7. And that happens when you have a term that's both top and bottom that cancels out, whether it's an x over an x, that kind of thing. Any of those, anything that cancels out that's a factor top and bottom would be that. All right, so let's look at something quite a bit more complex. Oop, I did not want to do that. I knew that was going to happen. All right, so going over here, I'm going to move this way a bit. And I'm going to do that. All right, so we're there. And let's do that. And let's look at a new function. Y equals x plus 3 times x minus 2 times x plus 1 all over x plus 2, x plus 4. So we want to find any asymptotes or holes for this graph. I'm sorry, I did that wrong. This is x minus 2. All right. So the first thing I look at here is that we've got a shared factor top and bottom. So I know there's going to be a hole at x equals 2, whatever makes this 0. So those go away. So this thing is going to look like these two multiplied. And if I multiply these two, I would get what? X squared plus 3x plus 1x, so plus 4x, and then plus 3. So it's going to look like that over x plus 4, right? So what does this tell me? Well, first off, it tells me a vertical asymptote is going to happen when x plus 4 equals 0. So that's at x equals negative 4. So at x equals negative 4, I know I've got a vertical asymptote. And in terms of a horizontal asymptote, well, if I divide x plus 4 into x squared plus 4x plus 3, I would get x. That gives me x squared plus 4x. So that becomes 0 plus 3. This does not go into 3, so we have a remainder of 3 over x plus 4. So this is going to look, I'm sorry, the horizontal asymptote is going to be what? There isn't one, right? This was a degree higher on top than the bottom. So we get instead a slant asymptote. Slant asymptote is going to be y equals x, right? Again, this is going to be the difference between the graph and y equals x. So y equals x comes through here as a slant asymptote. Oh, I'm veering off a little bit. So we have these things as our slant asymptotes, and we can get a picture of this on our graphing calculator if we wanted to. If we graph the original function, and let me turn this back on, we graph the original function. On top, we would have, I'm going to do a double parenthesis. I'm going to write this in just like it is. X plus 3 times x minus 2, and I'm going to put that in there, x minus 2 times x plus 1, and then close that top, and then divided by, on the bottom, x minus 2 times x plus 4. And I am going to go down and clear out that one too, so I don't have that in there. and graph this. And what I see is that slant asymptote. All right. And we see the behaviors up in this quadrant and down in that quadrant. But we know there's a hole at x equals 2. So what value would we put the hole at? Where do we put the big circle? Well, we find that by plugging this in to whatever one you want to. We can plug it into here with these two pieces. If we do that, it would be y equals 2 plus 3 is 5 times 2 plus 1 is 3 over 2 plus 4 is 6. So this would be 15 over 6, which is what? 5/3. So at 2 5/3, I'm going to have a hole, which would be about, let's see, 2, 1 and 1/3. It's going to be just above this thing, right? Just here. And this is coming in this way, and then looping around that way. And then the other piece is going down here. And we would have our graph. All right, that's about as ugly as it gets. Again, guys, this is going to take some practice. So do not skip these. Make sure you go through, get some good practice on them. And we will handle questions tomorrow. All right, so have a wonderful day, and we'll talk then.